Good morning, grade 9. Hope you are all doing well. This is Miss Pamela Teeny giving the physics course. Today we are going to start with section 2 in chapter 5, talking about applying Newton's laws. If you all can please open your books on page 161 so you can follow up with me. This section includes several ideas talking about how we apply Newton's laws. Today we are going to talk about the first one. The first one is about diagramming forces. So when solving a problem involving Newton's laws, it's helpful to make a sketch showing the relevant forces. A sketch that shows all the forces acting on an object is referred to as a free body diagram. To simplify the drawing, we often represent the object with a point. So a free body diagram is a sketch that shows all the forces acting on an object, and the object is represented as a point in order to simplify the drawing. So in solving problems that involve Newton's laws, the first thing you can do, or you should do, is drawing a free body diagram. In the figure in front of you, you can see two examples of free body diagrams. The first one is a free body diagram of an object at rest on a surface, and the second one is a free body diagram of an object in free fall. So in the first one, you can see the object is represented as a dot, and the forces are represented as vectors. Since the object is at rest and on a surface, then two forces act on the object and they are equal in magnitude but opposite in direction. So the vectors representing the forces are equal in magnitude and opposite in direction. The first force is the gravitational force exerted by Earth on the object, and the direction is downwards because the gravitational force pulls the object downwards. And the second force is the normal force, and it is exerted by the surface on the object, and the direction is upwards. In the second example, which shows a free body diagram of an object in free fall, we already know that an object in free fall has only one force acting on it, which is gravitational force. So since here we ignore air resistance, we can see that the free body diagram shows the object as a dot and only one force acting on it, which is gravitational force exerted by Earth on the object, pulling it downwards. Once all the forces are drawn on a free body diagram, a coordinate system is chosen and each force is resolved into its components. At this point, Newton's second law can be applied to each coordinate direction separately. As you can see in the figure in front of you, a box is on an inclined plane, which is a tilted plane or a tilted surface. And you can see the free body diagram of the box showing three forces acting on the box. And the coordinate system is chosen, which are the x and y axis. So the x-axis is parallel to the plane, and the y-axis is perpendicular to the x-axis. So each time you draw the free body diagram, you have to choose the most appropriate coordinate system. To see how this works, consider a situation where two astronauts are using jetpacks to push a 940 kilogram satellite toward a space station. The physical system and the free body diagram are shown in the figure below. As you can see in the figure in front of you, to the left you have the physical picture, which is simply an image of the situation, and to the right you have a free body diagram. In the free body diagram, the object, which is the satellite, is represented as a dot, and the forces are represented as vectors coming out of that dot. The first force is of the first astronaut to the right, and the second force is of the second astronaut upwards. And the coordinate system is chosen appropriately according to this free body diagram, as you can see in the figure in front of you to the right. So with the coordinate system that is used in the figure, astronaut 1 pushes in the positive x direction, which is horizontally, and astronaut 2 pushes in the positive y direction, which is vertically. Now, if each astronaut pushes with a force of 46 newtons, what are the magnitude and the direction of the satellite's acceleration? So in order to calculate the magnitude and the direction of the satellite's acceleration, there are several steps that you need to follow. So please concentrate with me. In order to solve a problem like this, we treat each coordinate direction independently of the other. First, we resolve each force into its x and y components. The first force acts only on the horizontal, so it has an x component equal to 46 newtons, and the y component is equal to 0. However, the second force is only on the vertical direction, so its x component is 0 and its y component is 46 newtons. Please recall the lesson in which we studied about resolving vectors. So if you can look at the figure in front of you, F1 has an angle of 0 and F2 has an angle equal to 90 degrees. And in order to find the x and y components, we use the following equations, which we already took and studied and did several examples about. So the x component is Rx equal to R times cosine angle. R is the magnitude of the vector and the angle is the direction of the vector. And the y component is Ry equal to R times sine angle. After we resolve each force into its x and y components, we find the acceleration in the x and y directions by using Newton's second law, which states that the net force acting on an object is equal to the mass of the object times its acceleration. So the acceleration in the x direction is equal to all the forces in the x direction over the mass of the object. And the acceleration in the y direction is equal to all the forces in the y direction over the mass of the object. In this situation, all the forces in the x direction are 46 Newton plus 0, and all the forces in the y direction are 0 plus 46 newtons. So the accelerations in the x and y direction are equal in magnitude, which are equal to 0.049 meter per second squared. In the third step, we use the Pythagorean theorem to find the magnitude of total acceleration. So we have the acceleration in the x direction and we have the acceleration in the y direction. We use the equation shown in front of you in order to find the magnitude of the total acceleration. Acceleration, which is the total acceleration, is equal to radical acceleration in the x direction squared plus acceleration in the y direction squared. We put the values and the answer is 0.069 meter per second squared. In the fourth and final step, we use simple trigonometry to find the direction of acceleration. So we already found the magnitude of acceleration. Now we need to find the direction of acceleration because it is a vector and thus it has a magnitude and a direction. So the direction, which is the angle, is equal to tangent minus 1. In order to put tangent minus 1 on the calculator, we put shift and tangent into A, acceleration in the y direction, over acceleration in the x direction. So in this situation, the angle is 45 degrees because both accelerations are equal. As a homework, please draw the free body diagram of each of the following objects. A ball in free fall, ignore air resistance. B, a box being pushed to the right. C, a box at rest on a table. Number 2. Two forces act on a box as shown in the figure below. Find the magnitude and the direction of the total acceleration of the box. Please, in order to solve this problem, follow the 4 steps that I explained to you today. I need your homeworks to be done and submitted to me by Friday, 27 March. Thank you and good luck.